This video contains a solution for number 11 from your multiple choice 7172 packet, but in fact number 11 that was snuck into this packet, it really is from section 7.3, which is a section we're not going to cover in detail because it's really not something that is emphasized in our curriculum or is part of it at all. So if you're interested, I'm just going to very quickly go through what the 7.3 notes would look like, and I'll use number 11 as an example for that. So number 11 says the region of the first quadrant between the x-axis, the graph of y equals 6x minus x squared is rotated around the y-axis. Let's see what that looks like. The intercepts of this are 0 and 6. And region in the first quadrant between, oh sorry, it's upside down. So it'll be like this, right? Setting that equal to 0, find that ours is at 0 and 6. So if we rotate that around the y-axis, we get something that looks like this. If you know what a bundt cake is, it looks like a bundt cake pan. It makes it sort of like a coffee cake shape. So it looks something like that. Now here's the problem. If we take, since we're, you might think, well, we're rotating around the y-axis, so that's just going to be like a dy problem. But here, if we sliced across like this, the problem is the inside, you can see there's definitely a hollow part, the inside and outside radius would both be part of the same function. So it turns out that method is not a good one for doing this. What we're going to do is this. Instead of slicing it this way, we're going to make it from little shells, cylindrical shells. So consider this. Consider this little piece of this thing, like a little cylindrical shell, right? And as we go from here to here, the shell would go from having a height of 0 up to here and then back down to here again. And if we took the volume of all of those cylindrical shells, almost like we were making it out of little like paper mache cylinders, right? Just like adding a little bit each time we go around. So if we took the volume of all those cylinders, then we'd get the volume of the whole thing. So let's pull that one cylinder out and see if we can find its volume, and then go from there. Let's see if I can make a reasonable sketch of that. So each one of the cylindrical shells looks kind of like this. Now what we're going to do is we're going to make a cut here, just as if this were one of those little paper loops that you might have made in art class in 2nd grade or something. You made like a paper chain. We're going to cut right here, untape it, and turn it into a little cylindrical slab. Not a cylinder, it's not cylindrical anymore. It was. Now we're going to unwrap it like that. So this is cut here and then unwrapped to be this. Let's find the dimensions of this little rectangular box here. This is the tiny little dx, right? That's like getting infinitesimally small as we do our calculus limit thing. This height right here, well, that's the value of the function, right? That would be f of x. And this here would be the circumference of this. And circumference is 2 pi r, so it'd be 2 pi times the radius of this, and the radius of this is the x value, right? So it'd be 2 pi x. Now the volume of this, of any one of these, is equal to the 3 dimensions multiplied together. So that's be 2 pi times x times f of x dx. And if we want the volume of the whole thing, we get to let the x values go all the way from here to 6 in this case. So it's going to be, since that's just a constant, I can put that on the outside of the integral. So it would be from wherever to wherever, a to b in general, of x times f of x. So just like in 7.2, when we think of our volume function, this is just our little thought bubble here. We think, okay, we were doing volumes like this. They were basically like pi times f of x squared dx. That's because our cross sections were circles, and the area of a circle is pi r squared. But now they're areas of these little rectangular slabs, and the area of those, it's the circumference times the function. So it's 2 pi r times the height, which is the function. And that's how to understand that formula. So in this particular problem, that means we've got 2 pi times, and notice here that even though we're rotating around the y-axis, this is a dx problem because our little slices are little tiny dx's. So that's a very sort of different feel with these. If you're going to do volumes by cylindrical shells, then rotating around the y-axis is actually a dx problem, and vice versa. Okay, so we get 2 pi times x times, in this particular problem, the function was 6x minus x squared dx. And all they wanted here was for you to know how to set it up, not actually get the answer. So that's answer choice B, but there's really no way you could have done that one without having these notes. So that's how you set something up like this. Why are we skipping that? Because it's really not something that you are going to see, and it's not a technique that we use too often. So if you're interested, you can file that away, but there's about a slim to none chance that you're going to see that on the AP test, and it's not something that I'll assess on our Chapter 7 test. Okay?